This one is 2.18. Here there are two linear springs of different coefficients or spring constants K1 and K2, and they are connected in series. Okay, and we have to calculate the overall spring constant. So for overall spring constant, what we can assume is that there is this effective spring sitting here which has the same force F. And if we can find out how much this deforms, and if we can write a relationship between this F and delta, this proportionality will be defined by the effective coefficient, which is K, and this is what we are interested in. So for the given system, there is a support here. Now if I consider this whole thing as one system, the reaction at this support is going to be same force F. Now hypothetically, if I cut these two springs and keep them separate, your first spring will have force F coming from here and a force F to balance it out. Now similarly, your second spring here will have this force F coming from the bottom and F at the link point. Now you can see in series both the springs are going through the same force, right? Now if I see the deformation delta 1 in the first spring, it is going to be F divided by K1. Similarly, delta in this second spring here is going to be delta 2, which is F divided by K2, because the spring constant here is K2. Now for this case here, the total deformation or the total amount by which this point is going to move is going to be delta, which is a summation of these two individual springs. So if I do this, I can write down from here value of delta 1 and value of delta 2 from here, and this delta value on this side I can pick up from this relationship, which is F divided by K. Now in here we can cancel these three F's here, so that your 1 over K is equals to 1 over K1 plus 1 over K2, which is that famous relationship for springs in series, which can also be written as K equals to K1 K2 divided by K1 plus K2. So that's the effective spring constant when two springs are in series.